Okay, so I'm going to commence with chapter 6. Later on, I'm going to make announcements about your upcoming tests, so um, stay tuned for that. So, chapter 6 deals with this area of chemistry known as thermochemistry, and as the name suggests, basically this is where we're going to deal with energy changes that takes place in a chemical reaction, right? So we have to go back to the fundamentals and we have to define certain terms. The first of which is energy. What do we mean by this term? Energy is basically the capacity to do work, which means basically the capacity to move something over a particular distance, right? So if I push on an object like this button right here, right, I'm performing work on the object because I've pushed it and it moves a certain distance, and therefore what I've done is impart energy to it. All right. So that's basically what the term energy means. And just a little bit more information here. Energy literally means work within, but that's a bit of a misnomer because the object that is subjected to energy input, it does not contain work, it will gain energy. All right. So as far as energy is concerned, there are two main types. You have potential energy, which is the energy an object has by virtue of position or composition. And then you have kinetic energy, which is the energy an object has by virtue of its motion. All right. And there's a formula that we use to calculate the kinetic energy, which is given right here. It's half mv squared, where m, units of m would be kilograms. So m would be in kilograms, and v, the velocity, would be in meters per second. So therefore, using these units, then the energy units would be kilograms meter squared over second squared. And this collection of units is given one unit symbolized by the letter J, which is the joule unit, right? So the joule unit is the same thing as kilograms meter squared over second squared, right? Okay, some other basic terms. So as I said before, thermochemistry is where we're concerned with energy changes that occur during a chemical reaction. So there are some terms that you need to be aware of that we'll be using from time to time in this chapter. The first of which is when we talk about the system or a system, basically we're just talking about a particular part of the universe that we're studying. All right, so that could be anything from a test tube to a beaker to a big vat or whatever is going on and whatever we're interested in, and whatever we're studying as far as that is concerned, then that would be considered to be the system. And then the surroundings would be basically, in that context, the rest of the universe, right? So basically, the system plus surroundings would be basically the universe, right? So when it comes to types of systems, there are three types, right? You can have what is known as an open system, where there will be an exchange of energy and matter between the system and the surroundings, right? So we say that's an open system. And then in the case of a closed system, you can have the exchange of energy between the system and the surroundings, but there won't be any exchange of matter between the system and surroundings, right? And then the third and final type of system is what we call the isolated system. In the case of the isolated system, there's no exchange of matter or energy between the system and the surroundings, all right? So that's basically the three types of systems. So the example that is shown here is of a jar containing honey, which is sealed, right? So this is a closed system based on what we just said before, because for one, matter will not be exchanged between inside and outside the jar, but you can have energy either entering the jar from outside or energy leaving from inside to outside the jar, because the walls of the glass jar would allow that, right? So that's what we call a closed system, right? And this diagram here is basically further illustrating what a closed system is. Now, a question is being asked. After the lid of the jar is unscrewed, which kind of system is it? So what do you think the answer is?
Open.
Open system, exactly. All right, so much for that. Some other terms that you need to be aware of. Internal energy, all right? That is the total energy that is contained in a system. And conventionally, we use the letter U to represent it, but I've also seen that in some chemical literature textbook and so on, they use the letter E. So U or E can be used to represent internal energy. And as far as the different types of energy involved to contribute to the total internal energy, part of it will be kinetic energy, which results from molecular motion. And these types of energies would be of the form that would be a combination of translational, rotational, and vibrational motion, right? So collectively, these types of energies collectively would be called thermal energy, all right? And the reason why primarily is because there is a relationship between the energy, kinetic energy, vibrational, and so on, with temperature, right? So we call that thermal energy. And then we have another part of internal energy, which is potential energy, which is due to intermolecular and intramolecular forces of attraction, and also related to the location of atoms and bonds. And sometimes we call these types of energy chemical energy, all right? And then another term we need to be aware of, heat. Heat is, technically speaking, not energy. It's basically, how should I put this? It's a transfer of energy from one region, which is hotter, compared to another region, right? So basically, if you have two objects in contact with each other, and one object is of a higher temperature than the other, then basically the heat energy would flow from the hotter object to the cooler object, all right? And that will continue until both objects are of the same temperature. When that happens, then we said that the system will achieve what is called a state of thermal equilibrium. And to illustrate this at the microscopic level, we have this diagram right here, where we have argon atoms here on one side of this hypothetical thin wall. And the assumption is that you can have basically heat transfer through that thin wall to the other side, which has nitrogen molecules, all right? So let's say the argon molecules are more energetic compared to the nitrogen molecules, right? That basically means that the argon molecules or the argon gas over here would be of a higher temperature compared to the nitrogen gas on the other side. So therefore, as I said before, the heat will flow from the more energetic higher temperature molecules to the less energetic lower temperature molecules, right? And that heat flow will continue until both sides will have the same temperature. Now, a question is being asked here. How do the root mean squared speeds of the argon atoms and the nitrogen molecules compare at the point of thermal equilibrium? Well, if you remember, well, one way of looking at it is that the kinetic energy is equal to half mv squared. Now, in this context, we can use the root mean squared to represent v squared, all right? So basically, in the case of argon, then we can use that symbolism. And in the case of nitrogen, we can write down a similar formula. Oops, and equal to half m mean squared speed for 1 minute, and use to change this symbol here to here, and this would be for nitrogen, right? Oh, and by the way, I should also include the mass of argon here and the mass of nitrogen here, right? So to answer this question, what will happen is that the energies will be the same, right? The kinetic energy of argon and nitrogen will be the same. In fact, let me get out of this here and just since I need more space, so let me so as I was saying, the kinetic energy of argon will be equal to half the molar mass or the mass of the argon atom times the root mean squared this of the argon atoms, and the same is true, or something similar is true for nitrogen, half m n2 times the mean squared of n2. So as I was saying, at the point of thermal equilibrium, the kinetic energy of argon will be equal to the kinetic energy of nitrogen, right? So that would mean that half m argon B argon, or I should say U squared bar argon, will be equal to half M nitrogen U squared nitrogen. So if that is true, that means that the halves will cancel out. And what was the question asking? The question was asking, let me go back to it. The question was asking, how do the root mean square speed compare, right? So what we can do is divide both sides by U argon squared, and also divide both sides by m and 2, m and 2. So this will cancel with that. This will cancel with that. So you're going to end up with the mass of the argon atom divided by the mass of the nitrogen molecule will be equal to the mean squared average of the nitrogen molecules divided by the mean squared average of the argon atoms. And all we have to do is consult the periodic table to look up the molar masses of argon and nitrogen. So argon has a molar mass of 39.95 AMU, and the molar mass of nitrogen would be 2 times 14.1, which would be 28.02 AMU. So that would give 39.95 divided by 28.02. So according to my calculations, when rounded off to 4 sig figs, that would be 1.426. So therefore, the root mean squared speed, or the squares, root mean squared speed of nitrogen would be equal to 1.426 times the root mean squared speed of argon, right? So basically the nitrogen molecules will travel at a higher speed to this extent compared to the argon atom, which makes sense because the nitrogen molecules would be lighter, right, compared to nitrogen. So at the same temperature, the argon, the nitrogen molecules will travel at a fast speed. Okay, so that's a bit of a detour. So let me, any questions about what I've just done? Any questions? Any questions? Okay, so let me go back to the PowerPoint. Okay, so we talked about work already. Right? So basically work is like heat, representing a heat transfer between a system and surroundings, all right? Now, the difference between heat and work in terms of energy transfer is that work is caused by applying a force to an object and the object moving a particular distance, right? So that's basically how work is calculated. If you apply force to an object and it doesn't move, it doesn't matter how large the force is, you're not applying work or you're not imparting energy from work to that system, right? Work is only done if you apply force to the object and the object moves the distance, right? So the difference between heat and work is force is applied and the object moves the distance, whereas heat is caused by a temperature difference that would occur between two different systems in contact with each other, all right? Now, what you're going to see is that the sign of the energy changes will become important when it comes to problem solving exercises, right? So it says here that a negative quantity of work signifies that the system loses energy, right? So basically if the system is doing work on the surroundings, then that means that the system will be losing energy in the process. On the other hand, if the surroundings is doing work on the system, then the system will be gaining energy as a consequence of that. All right. Now, in reality, there's no such thing as negative energy or positive energy. The actual sign basically represents the energy flow, right? So if you do a calculation and you get a negative energy value, what that means in practice, in reality, is that the object is or the system is losing energy. Or on the other hand, if a system is gaining energy as a result of whatever process that may be occurring, that means that work is being done on a system and therefore there's an energy increase. And therefore, mathematically speaking, that sign would be positive. Okay, so just to give some illustration of what I just mentioned, let's look at this particular setup right here. So what we have here is a gas that is trapped in this container. And these are all, not realistic, hypothetical situations, right? Because basically what we're assuming is that this plate here can move freely without any friction, right? And we have the gas trap here. And let's say that the gas expands from an initial volume here to a final volume here, right? So basically there'll be a change in the volume of the gas, right? To calculate the work that is done on the gas, this would be the formula that you use. The work will be equal to minus P times delta V. And the reason why we have a minus sign here is because the gas is expanding. So the work that is done on the gas would be considered to be negative. All right. And as a result, because it's negative, then basically the gas will be losing, or the system will be losing energy as a result of that. Now, if it was the other way around, then basically what will happen is that there will be a decrease in the volume. If the volume decreases, if the volume decreases, that means that delta V is negative, which means that if this is negative and that's negative, that means that the work done on the gas will be positive, right? And therefore, what that means is that the gas will, or the system will gain energy as a result. All right. Okay. Some other terms that you need to be aware of when we talk about the state of a system. Basically, what we're talking about is the exact condition of that system at a particular fixed instant. So that state can change with changing, several factors, temperature, and whether or not it's a solid, liquid, or gas, or if you do literally anything to it, basically that state will change, right? And as stated here, the state is determined by several things, many things, by the kind and amount of matter present, the structure of this matter, the molecular level, and the prevailing pressure and temperature, all right? And then we have what is called a state function. A state function is basically a quantitative property, which means that it can be measured. That has a unique value and that depends only on the current state of the system. And this is very important, does not depend on how the state was reached. In other words, it does not depend on the history of the system, right? So that's what we mean by state function. And there are several state functions that we can talk about. We're going to talk about a couple of them in this chapter, but just to mention a few: internal energy is a state function, temperature is a state function. Later on, we're going to learn about enthalpy, volume is a state function. So there are several things, anything that is dependent on the current state of the system. Okay, now there's one law that we're going to talk about here in this chapter, and that is the law of conservation of energy, which is also known as the first law of thermodynamics. There are actually three laws, right? We're only going to deal with one of them in this chapter. For those of you who have to do general chemistry too, there is another chapter which deals with thermodynamics, which you're going to, again, revisit this law, but you'll also be introduced to the other two laws, all right? But for now, we're just going to focus on the first law of thermodynamics. And basically what this law says, simply put, is that energy cannot be created or destroyed. Now, this is an oversimplification because this only applies to chemical or physical processes. It doesn't apply to nuclear reaction, which we won't get into here, all right? So the inference or the conclusion that we can come to based on this law is that the internal energy change in a system is simply the difference between the energy of its final and its initial state, right? So basically, the change in internal energy will be equal to the internal energy value that is final minus that which was the initial internal energy, all right? An additional conclusion we can come to is that this energy change that we just talked about occur only if the energy change, I should say, that we just talked about, if it occurs only as heat or work, then the relationship between this delta U value here and heat and work is given by this equation. Delta U is equal to Q plus W, right? So basically what this is saying is that the change in internal energy is equal to the amount of heat change for the particular system plus the amount of work that is done on the system. That's basically what this equation is telling, all right? So that's the result of the first law of thermodynamics. Now, it's very important when applying this equation that you pay attention to the signs, especially when you're given a question and the question gives you the information in words. You have to basically interpret that question in terms of the signs for delta U, for Q, and for W, right? So the sign convention is very important when it comes to certain problem solving. So basically what you need to recognize is that if you have energy entering the system, right, then that could be due to heat being absorbed by the system or work done on the system. In either case, the energy change will be positive for that system, right? If energy is applied to a system, then the energy change would be positive. On the other hand, if energy is leaving the system, then that could mean one of two things or both. It could mean that heat is given off by the system or work is done by the system. In either case, energy change in that particular case would be negative. So it's very important that you understand how to interpret the sign of the energy change in terms of whether or not energy is leaving or being absorbed by the system, all right? If energy is entering the system, then the energy change would be positive. If energy is leaving the system, then the energy change would be negative, all right? So to apply what we've just learned here, let's look at this question. And again, you have to pay attention to how the question is worded so that you can use the appropriate sign. Now, the equation that we're going to use to solve this problem, I'm going to write it here. Same equation I showed you earlier, which is U is equal to Q plus W, all right? So the question says, a gas does 135 joules of work, right? Very important. In fact, let me circle does right here, right? While expanding, and at the same time, it absorbs 156 joules of heat. So the question is, what is the change in internal energy, right? So the question is asking for U, and the question gives you the amount of heat change for Q and for W, right? Now let's look at W first, since that's the first information here that is given. When the question says that the gas does 135 joules of work, what does that mean for the sign associated with that work?
Negative.
Exactly. So that means that W is equal to minus 135 joules, right? And then it says here that at the same time, it absorbs 156 joules of heat. So what does that mean for the heat change? Is that negative or positive? It's gaining energy, so therefore, positive 156 joules, right? So therefore, U would be equal to Q, which is plus 156 joules, minus, or I should say plus, minus 135 joules. And that's it. So 156 minus 135. So according to my calculations, this works out to be equal to 21 joules. And that's how you do that, right? So whenever it comes to solving problems of this type, make sure that you read the question carefully so that you understand the sign that you should use for the different numbers. In fact, let me give you assignment 6 right now to get you started on this, because the very first question is kind of similar to what I just did here. Take one of this down. Take one of that down. We do. And for you guys out there in Zoom, I'm going to publish, if I'm not done so already. Okay, so let me go here. Go here. Okay, so let me publish that. And there's also another link, which is an additional. I'm going to publish that as well. All right. I think I have both of them in the documents that I've passed out in this class. So let me open this up. All right, so, okay, so number one, that's what we're going to look at now. This question says, calculate the total change in internal energy. They use delta U. We're using delta, I'm sorry, they're using delta E. We're using delta U, it's the same thing. Of a system when 400 joules is applied to expanding oxygen and the gas does 35 joules of work on the surroundings. So again, you have to pay attention to wording. All right. So delta U is equal to Q plus W. Okay, so in this particular question, look at how the question is worded. And I want you to tell me, firstly, what is Q equal to? Positive 400 joules, correct? And what is W equal to?
Negative 300.
Exactly. So delta U would be equal to plus 400 joules plus minus 350 joules. So that would be equal to 50 joules. And that's it. All right. So again, you have to pay attention to how the question is worded so that you know what signs you would use for both Q and W. All right. Okay. Any questions about that one? Any questions? All right, let's look at the next one, because the next one is based on a formula that I've introduced to you earlier. In fact, let me clear this. Scroll down. Okay, so the question is asking for you to calculate the kinetic energy in different units. All right. So the formula that you're going to use is kinetic energy is equal to half mv squared. If you remember, m is the mass in kilograms, and the velocity would be in meters per second. And if you use those units, then kinetic energy would be in joules. So in this particular case, they gave you the mass of a particle and they gave you the velocity, right? So the kinetic energy in this case would be half of the mass. Now they gave you the mass in grams, so you have to convert that to kilograms. 9.11 times 10 to the minus 28 grams. You have to convert that to kilograms, which means you have to multiply this by 1 kilogram divided by 1,000 grams. And then you multiply by the velocity squared, which is 6.00 meters per second, and then all of that squared. And then we do the number crunching, so I'm going to work out the squared part first. Oh, I forgot. Oh, I made a mistake here. This should be 6.00 times 10 to the 5 meters per second. And then that is squared. Okay, so 6.00 times 10 to the 5 squared. And then I'm going to multiply that or divide back by 1,000, then multiply by 9.11 times 10 to the minus 28. And then I'm going to divide by 2. And according to my calculation, please correct me if I'm wrong, this works out to be equal to 1.64 times 10 to the minus 18 joules. All right. So that's answering the question in terms of joules, but it also is asking for the answer in terms of kilojoules, which means that I would have to multiply this by 1 kilojoule divided by 1,000 joules. So basically, you're going to divide that answer by 1,000. And when I did that, I got 1.64 times 10 to the minus 21.
Is that 100 joules or 1,000?
1,000.
Okay.
Yeah, 1.64 times 10 to the minus 21. Kilojoules. All right. And then further, we're asked to determine the energy in calories. Now, if you look up in your packet, 1 calorie will be equal to 4.184 joules, right? So basically, I'm going to take this value here. I'm going to take this value here, which is 1.64 times 10 to the minus 18 joules, and I'm going to convert it to kilojoules, where I'm going to put 1 calorie above, and below I'm going to put 4.184 joules below. So let's see what I get. 1.64 times 10 to the minus 18 divided by 4.184. And according to my calculation, when rounded out to the free sig figs, that's going to be equal to 3.92 times 10 to the minus 19 joules. And that's basically how that is done. All right. Okay, any questions about this one? Any questions? Any questions?
Would that be calories or meters?
Calories, sorry, my bad. Thank you. So 19 calories. Okay, any other questions about it? Any other questions? Okay, so let me go back to the PowerPoint. Well, let me clear this first. Let's move on to heat of reactions, right? So basically, you're going to learn here the fact that when you have a reaction taking place, you can have a heat change, right? You can have a situation where you mix two things together and it produces energy, heat energy, or you can have a situation where you mix two things together and it absorbs energy from its surrounding, all right? So let's define some terms here. Q reaction is what we call the heat of reaction, right? And it's the amount of heat that is exchanged between a reaction system and its surrounding, right? Now, if you have a situation where a reaction produces heat, then we say that this reaction is exothermic, right? So basically, that reaction is producing heat, and that heat is basically given to the surrounding, right? Now, in an isolated system, what will happen as a result is that the temperature of that system will increase, right? And what will happen is that the system will go from a higher to a lower energy because the Q reaction in that case will be negative. So a good example of this would be, for example, if you take, well, this is technically not a reaction, but this illustrates the point of what happens when heat is given off. If you take, let's say you take a few pellets of sodium hydroxide and you place them in a test tube with water and you stir it to make sure that it dissolves, what will happen eventually if you feel the outside of the test tube is going to feel warm or even hot. right? Depending on the amount of sodium hydroxide you use, okay? So that's an example of an exothermic process, right? Because it generates heat as the process takes place, right? Now, on the other hand, you can have a situation where a reaction will absorb heat from its surroundings, right? And we say that such reactions are endothermic, right? It absorbs heat, and therefore we say the reaction is endothermic. So in an isolated system, what will happen in this particular case is that the temperature will decrease, and that's because the system goes from a from a lower energy state to a higher energy state in order to absorb heat, right? And therefore, the heat of reaction in that case would be positive, all right? Again, another example of this, which is again technically not a chemical reaction, but it illustrates what happens when a reaction is endothermic. If you take potassium nitrate and you add it to a test tube of water, and you stir it to make sure it dissolves, then what will happen is that when you feel the outside of that test tube, it's going to feel cold, right? And the reason why, or cold, depending on how much of the potassium nitrate you use. And that is due to the fact that that dissolution process absorbs heat. So therefore, it's going to suck heat from your hand, and therefore that's why it feels cold, right? So that's the difference between an endothermic and an exothermic reaction. So to illustrate, in the case of an exothermic, what will happen under different situations, we have this hypothetical situation, which is pretty much, purely hypothetical, not what happen in reality. And then we have this, which will be a more common observation. And then we have this situation where we have the reaction taking place in an isolated system, right? So in the case of a hypothetical situation where this container is such that all the heat will basically escape into the surroundings for an exothermic reaction, basically what will happen is that there will be no temperature change as far as this reaction is concerned. So if the initial temperature is 25 degrees, it's going to remain at 25 degrees because basically the heat generated will escape and get into the surroundings, right? That is very unlikely to occur in most cases, right? What is more likely to occur is what is happening here in this middle setup right here. So what will happen is that some of the heat will escape in most cases, but some of the heat will be absorbed by what is left inside that container. And basically the result of that is that there will be a corresponding temperature increase from whatever it was before, presumably 25 degrees Celsius, to 32.2 degrees Celsius in this particular case, right? So there will be an increase in temperature as a result of some of the heat being absorbed by the contents that are remaining in this container. And then we get over to this, which is a very extreme case where none of the heat is allowed to escape because this is an isolated system. So basically what will happen is that the reaction will take place, produces heat, the heat won't be able to escape, so therefore whatever is left in there will absorb the heat, and therefore as a result, the temperature here will be higher compared to this particular system right here, all right? So that's what happens in the case of an exothermic reaction, and one can explain, if you understood this, one can explain what will happen if this was an endothermic reaction, which I won't get into right now, all right? Okay, so let's talk about some other aspects of this topic. We're going to look at what happens when you have an internal energy change, when the volume does not change, right? So basically, we're going to go back to an equation that we saw earlier, which is delta U is equal to Q plus W, right? Now, W, let me write this down here. So remember now, delta U is equal to Q plus W, right? Now, W, if you remember from earlier, that will be equal to minus P delta V, right? So therefore, we can rewrite this equation as Q minus P delta V, all right? And that will be equal to delta U. Now, if we're saying that delta V, if we're saying that the volume does not change, what that means is that delta V here would be equal to 0. So if delta V is equal to 0, what that means is that all of this will be equal to 0, which means that delta U will be equal to Q, right? And we represent that as Q sub V. The sub V basically means that the volume remains constant, right? So what does that tell us? That tells us that if the volume does not change, and there's a change in energy, internal energy, that means that there will be no PV work done. In other words, let's say, for example, the system is absorbing heat, and delta U would increase as a result, which means that Q would increase, but because there's no change in the volume, or because the volume is constant, well, that means that there's no work being done. So therefore, all the internal energy would be basically the heat energy that is either absorbed or released, all right? So that's basically what happens at a constant volume. Now, that which I just described is basically one that is very unlikely to occur unless you, of course, design the experiment such that the volume doesn't change. What is more common is if you have a system undergoing a change when the pressure is constant, and not the volume, but the pressure, right? And this is true for most reactions, right? So going back to this equation we have here, delta U is equal to Q minus P delta V. So therefore, if there is delta V is not 0, then basically we can rearrange this equation to get an expression for QP. So QP is, of course, the heat change under constant pressure conditions, and that will be equal to the change in internal energy plus P times delta V, right? So this is more often occurring when you have a reaction taking place, where the heat of the reaction or the heat change of the reaction will be equal to the change in internal energy plus pressure times the change in volume, right? Now, how do we interpret this? Basically, most of the thermal energy, let's assume that the reaction is an exothermic reaction. Most of the thermal energy will be released as heat, but there will be some energy that is used to expand the system against the surroundings. In other words, to push back on the atmosphere in those situations, right? So that's basically how we interpret this equation. Some of it is used in terms of this here. Some of it is used to produce heat change, but some of it also is used to expand against the surroundings, all right? So this brings us now to another term, enthalpy. Enthalpy is basically the sum of the internal energy and the pressure volume product of a system. In other words, this is enthalpy right here, all right? Which is symbolized conventionally by the letter H, all right? So when it comes to, as we said before, a system where a reaction is undergoing a change under constant pressure conditions, then the QP, which is the heat change of the reaction under constant pressure conditions, would be equal to the change in the enthalpy, which is delta H, because and some calculus is involved here when it comes to deriving this equation right here, right? Basically, if I were to go through the steps, delta H would be equal to delta U plus P delta V plus V delta P times V, right? How many of you have done calculus? One? Okay, so this might go over your head. Anyway, basically you learn in calculus that this is what happens when you make changes to these, but because the pressure is not changing, delta P is equal to 0. So that means that this becomes 0. So therefore your equation for delta H would be equal to delta U plus P delta V, which is what we have here, right? Which is equal to delta H here, all right? So the change in enthalpy is equal to the change in internal energy plus P times the change in volume. So the example that is shown here is a reaction between magnesium and hydrochloric acid, which produces hydrogen gas, which expands against the atmosphere, right? So work is being done by the system against the atmosphere. So therefore, basically, we can calculate that heat change based on this equation right here, if you know what the internal energy is and the change in volume and the pressure, right? So as stated down here, most reactions occurs under constant pressure conditions and not under constant volume conditions, right? So therefore, most reactions, the enthalpy change that occurs is equal to the heat change that occurs. All right. Let me see what the time situation is. Okay. All right, so let's move on now to a more in-depth discussion of this term enthalpy. So enthalpy, for one, is an extensive property. What does that mean? It means that it depends on how much of the substances are involved in the particular chemical reaction, right? And also enthalpy is a state function because it depends on other state function. U, P, and V, the internal energy, pressure, and volume, are all state functions, which means that enthalpy is also a state function. Enthalpy changes have unique values, right? And these are basically can be calculated based on either measurements or if you're given some data values, you can calculate the enthalpy changes of reactions, and we're going to get into that later on. All right. Now, we can represent the enthalpy changes in a reaction by using what are known as enthalpy diagrams, right? And the way we use it is that we have to interpret it such that we can see the sign of delta H. If delta H is negative, then basically that reaction will be exothermic. If delta H is positive, then that reaction is endothermic. So these diagrams here are showing you what happens in the case of exothermic and endothermic reactions. The first one shows you what happens in an exothermic reaction. You're starting off with your reactants here, and then down here you have your products. So obviously the reactants will have a higher enthalpy value compared to your products. So to get from the reactants to products, there must be a negative change in the enthalpy value because, and you're going to see this throughout this chapter, whenever you're measuring the change of anything, including enthalpy, it's always the final value minus the initial value, right? It's a final value minus the initial value. So if the final value is less than the initial value, that means the change, in this case, delta H, will be negative, right? In this case, in the case of an endothermic reaction, as you can see here, the enthalpy of the products will be greater than that of the reactants. So if you're going to use the same convention, the final value minus the initial value, obviously that means that the delta H or the change in enthalpy for this reaction would be positive, right? So for exothermic reactions, the enthalpy change would be negative. For endothermic reactions, the enthalpy change would be positive, right? Now, what happens if the reaction reverses? Well, in terms of what happens to the enthalpy change. Well, what happens is that the sign will change, all right? So if you have a reaction going from, do I have an example here? No. Okay, so if I have a reaction going from A to B, and let's say delta H for this is minus 5 joules, right? That means going from B to A, delta H for that would be plus 5 joules. All right? So whatever delta H is for the reaction going in one direction, then the sign will change in the delta H value for the reaction going in the other direction. So obviously what this means is that in a cycling process, if you're going from A to B and then back to A, then the total enthalpy change of that would be 0, right? No change means no change in enthalpy. Oh, so I do have an example here. So here's an example. The reaction going from mercury to oxide to mercury and oxygen, that has been determined to be equal to, the enthalpy change that is, has been determined to be equal to plus 90.83 kilojoules, right? That's going from mercury to oxide to mercury and oxygen. To do the reverse reaction, the enthalpy change would be minus 90.83 kilojoules. So basically, the sign will change. The magnitude will remain the same, but the sign is going to change if you reverse the reaction. All right? So let's look at this question here, this example. It says, given the equation, and it gives you the equation, and it gives you also the change in enthalpy value here, which is plus 52.96 kilojoules. The question is asking for you to calculate delta H for this equation, all right? So before we get into, well, let me ask you this. I want you to compare this equation to this equation, and I want you to tell me two differences between those two equations. There are two differences. What are they?
The amount of moles.
You mean the coefficients?
Yeah.
Okay, what about the coefficients?
They're halved.
Exactly. So all the coefficients for the different substances in the original equation are half in this equation. So that's one difference. What's the other difference? What's the other difference? First difference is that all the coefficients are half. So what's the other difference between these two equations? Yes, sir.
B is decomposition
Okay,
going separating.
well, that's true, but compare that to the first equation. What's the difference?
Reverse.
Reverse, exactly. Right, the products of the original equation is the reactant and vice versa, right? So this begs the question, how do those two changes affect the delta H value so that you can get the correct delta H value here? Now, if you remember, we said that initially that the enthalpy change is an extensive property. What does that mean? It depends on the amount of substances involved, right? So what that means is that if I were to divide everything by 2 or multiply by half, same thing, right? That means that I'm going to get half H2 gas plus half I2 gas to give HI gas, right? So what that means for delta H for this is that that value is going to be half. So half of 52.96 kilojoules would be the enthalpy change of this reaction, because all I did was divide everything by 2, which means that the delta H value would have to be divided by 2 as well, all right? Okay, and then to flip this to get this equation where the reactants become the products and vice versa, this begs the question, well, how does that change the resulting delta H value? And if you remember, I said, if you were to flip the equation, the sign would be changed, right? So therefore, delta H for this reaction here is going to be equal to minus half of 52.96 kilojoules. So 52.96 divided by 2, and the minus sign in front of it will result in the answer being equal to minus 26.48 kilojoules, right? So that would be the answer that the question is asking for, which is the delta H of this equation. All right? Okay, any questions about this example? Any questions? Any questions? Okay. Let's look at the next question. It says the complete combustion of liquid. In fact, you know what? Let me pop this onto Word because I'm going to need some space. This one, copy this here, and paste it onto a Word document. Okay, so the question says the complete combustion of liquid octane to produce gaseous carbon dioxide and liquid water at 25 degrees and at a constant pressure of gives off 47.9 kilojoules of heat per gram of octane. Write the chemical equation to represent this information. Okay, now let me just say that to be fair to you guys, what the question is asking for is not just the equation. I don't think this question was written very clearly. So it's not just the equation it's asking for, it's also asking for the delta H value associated with the balance equation, right? Now, that brings us to the question, What is the equation? So I want you to look at this information here and tell me firstly, what are the reactants in this particular question? Because remember the question is talking about combustion, right? That should give you a hint as to what the reactants are. Okay, so what are the reactants in this reaction?
Liquid octane and
Okay, C8H18 liquid and what?
oxygen,
And oxygen. All right, which would be a gas, right? And then what would be the products of this reaction?
water and carbon dioxide.
Okay, so CO2 gas and H2O liquid. Okay, very good. And then we need to balance it. So how do we go about balancing this? How do we go about balancing this equation? Well, how do we go about balancing this equation? So put an 8 in front of the CO2. Anything else?
4 in front of H2O.
4? Sure about that? How many hydrogens do we have on the right, on the left side? I'm sorry.
8, 9, right?
18.
Oh.
So what would you put in front of the H2O?
9.
9. Okay, and then we have to balance the oxygens. So how would you balance the oxygens? This. How many oxygens do we have total on the left side? On the left side? 2, right? How many do we have total on the right side?
5.
25. So how do you propose we balance oxygens? Yes, ma'am.
When I'm getting tutored, the chemistry tutor says like, you can use fractions.
Yeah. So what would be the fraction that you use?
Yeah.
Anybody
I
want
know
to?
you use fractions.
You're right, right? You can use fractions, even though that would not remain in the final answer, but you're right, you can use fractions. So what fraction do you think we should use in order to balance oxygen? Now, where would we put it?
What if it's 25?
25 over 2, exactly. 25 over 2, because 25 over 2 times 2 gives you 25, which balances with the 25 on the right side. But we cannot leave this as it is. We need to make sure that all the coefficients are integers, right? So how do we ensure that?
Double every.
Double everything, multiply everything by 2. So the final answer, well, not the final, but the equation becomes 2C8H18 plus 25O2. And then on the right side, we're gonna have 16 CO2 plus 18 H2O. All right? So that would be the equation that we're gonna work with. Okay. Now the question says that, and again, reading this carefully, you have to make sure that you interpret the question carefully, right? The question says that the reaction gives off 47.9 kilojoules of heat per gram of the octane. What does giving off mean?
Negative, so it's a negative.
It's going to be exothermic, or it's going to give off heat, so therefore it's exothermic, right? So the first thing I would do is, now remember, the aim is to find out what delta H is here, right? So what I would do is, I would start off with 2 moles of the octane, and then I'll convert that to grams, which means that I'm gonna need molar mass, 1 mole of octane at below and above the molar mass, so again. What I'm gonna do is with my trusty molar mass calculator. C8H18. 114.23. So that is going to 114.23 grams of C8H18. So the moles will cancel out here and here. And then the next conversion factor is where we utilize this information right here, right? 47.9 kilojoules of heat given off per gram of octane. So the way we represent that here is that we're going to put minus 47.9 kilojoules over 1 gram of octane. And that's basically it as far as the setup is concerned. So 2 times 114.23 times minus 47.9. And that should give us our answer. And according to my calculations, now in this case here, I have to round off to 3 6 So I got minus 1.09 times 10 to the 4 kilojoules. And that's basically how that is done. All right. So basically delta H, you can place it as being equal to this value, minus 1.09 times 10 to the 4 kilojoules. All right. Okay, any questions about this? Any questions? 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 All right, let me continue. See what next. Okay, so I think this is going to be the last thing we're going to discuss today. We're going to look at how stoichiometry affects the use of delta H in calculations. All right. So basically, when it comes to solving problems involving enthalpy changes, you can look at heat change being a product in the reaction is exothermic, right? And then if the reaction is endothermic, you can look at the heat change as a reactant, right? And therefore we can generate conversion factors involving delta H based on the balance equation along with the enthalpy change value, right? So for example, if you look at this reaction, the reaction of hydrogen and chlorine to form hydrogen chloride, and the enthalpy change of that reaction was measured to be minus 184.6 kilojoules. Then you can use this along with the different terms here and their coefficients to write down conversion factors. For example, you can write down a relationship between the moles of HCl, or I should say the moles of H2, and this value. You can have minus 184.6 kilojoules over 1 mole of H2, or the other way around, depending on the type of calculation that you're trying to achieve. And you can do the same thing for the others as well, if HCl is involved, right? Or if chlorine is involved. But if the enthalpy change is involved, then you can write down these conversion factors as well. And therefore, you can use these to solve certain problems, such as this example right here. So let's look at this example. They gave you the same equation, actually, the balance equation, and they gave you the enthalpy change. And the question is asking, what is the enthalpy change associated with the formation of 5.67 moles of HCl? So basically what we'll do is, we're going to do this up here. We're going to start off with the 5.67 moles of HCl. And then you're going to multiply that by your appropriate conversion factor, which would be down here, you're going to have 2 moles of HCl because you have a coefficient of 2 here. And above, you're going to put this value here, which will be minus 184.6 kilojoules. Right? And that's it. So the moles of HCl will cancel out here and here. And you're going to end up with 5.67 times 184.6, and then divide by 2, and you will end up with minus 523 kilojoules as your answer to that problem. All right. So this is combining enthalpy changes with stoichiometry principles that you have learned from an earlier chapter. Okay, any questions about this? Any questions? All right, let me see here. Okay, I think I'm going to stop here for today. So before you leave, by way of announcement, 2 things. One, and I think I've sent this out to you guys before, I won't be available on Friday because I have a meeting to attend out of town. So I won't be available during my office hours. Usually I'd be available during my office hours at the Ocala campus or online, but not this Friday, all right? The second thing has to do with your test. Now, I think when did I say?
16, but you changed it to the 20th or something.
Oh, 1 minute. Okay, I think I've changed it in this announcement to the 21st. And the reason why is because, I'm trying to remember, did I send you back your graded assignments for chapters 3, 4, and 5?
No, I think 3 and 4, but I
Oh,
don't.
not 5, okay, yeah, you're right, because 5 is the one that you just submitted yesterday. Or the deadline was yesterday.
Something like that.
Right, okay, right. So, so I'm going to jump on that as soon as I grade some other stuff. Because I want you to get back those assignments so that you can have it to review in preparation for that test, right? So yes, the test will be based on chapter 3, 4, and 5. So you can review the assignment keys and your graded assignment. And I'm going to did I publish the key for assignment 5? No, I didn't. So let me do that now. All right. So you can have that to review as well. All right. So just to let you know, that's basically what the deal is. Your test will be basically next week this time. As soon as, and I'm gonna really get a rush on the assignment number 5 and get it back to you so that we can have that to look at as well. Okay, and I think that's pretty much all I have to say as far as assignments are concerned, as far as any other announcements. Unless there are any questions. Any questions?
Are you gonna post an old test again for this one?
We do that now. Okay, so pass test key. Okay, what did I? Hold on. Go back and see if I published that folder. Okay, so let me publish.
Test number 2. Can you advocate for me?
Okay, let me. Quick look at this one right here. Okay, so that's. Oh no, this is wrong. It's general construction. How did that get there? Let me unpublish that. Let me see what this says. Hold on, looks like I accidentally, you know what, let me get out of this here. I think I accidentally shift some past tests from general purpose to. So let me unpublish this here. Avoid confusion. And let me publish, let's see what it's one says before I publish it. Okay, test number 2. No, I came to stuff. Move. Let's see this one here. Okay, Chem 1 stuff. All right, let's see here. Okay, so based on what I see here. This test right here, which is what? This is, okay, good. Test number 2, all right? So let me just do a quick look. Okay, so yes, that could be on the test. That 2. That 2. That 2, balance and redox equations. That 2. That 2, that was shown. Gas laws. Okay, so this here is a very good, you know, past test to look at to prepare. So what I'm gonna do now is I'm gonna publish that photo. I need to get rid of those others, but that's definitely an error on my part. So I would, if I were you guys, I would look at this link here. Let me check out this one right here, test number 2, for 15. Okay, this is another good one as well. So yes, I will check out this one as well in preparation for your. Okay, now this one has what we just covered, which will not be on the test. Right, so question 3 here, dealing with thermochemistry, will not be on the test, right? But apart from that. So let me see, that's published. Okay, so this one here, I would strongly recommend that you check that out. Let me check out this one right here. Okay, that's okay. Okay. Okay, this is another one I will check out if I were you guys. Okay, so so these two here, these two test number 2, and which one did I say? Was it this one?
Pretty sure.
Yeah, so check out those, you know, those will help you as well to prepare for your test, all right? And of course, if you have any questions, feel free to contact me during my office hours, excepting this Friday. But, you know, I'll be available if you have any questions while doing those, all right? All right, so that's pretty much it for today. So, I'll see you guys on Thursday. Or, well, some of you I'll see that short. Okay, and you guys know there in Zoom, I'm signing off now.